take them down and take them down and take them down, take them down, take them down and take them down and take them down. As you look, the whole room explode down and as you look, the whole room explode down and
Okay, a couple of disclaimers first. First of all, as Jan said, I was planning on speaking in Hebrew. When I got here, I found out there's people who don't speak any Hebrew, and so I translated it all into English. So if I say something that doesn't make any sense, first translate it back into Hebrew, type it into Google Translate, change it back into English, and then you'll see what I had originally intended. If anybody has any questions in Hebrew afterwards, I'm very happy to talk about it. I learned the entire thing in Hebrew as well. Second of all of these pictures that I copied, I found on the internet, and I didn't have permission to take them. What I did to compensate was I put a link to the original picture on every slide. If you feel like it, go to the website and buy something from the company, and then I'll feel much better about doing that. In any case, I'm very excited to be here today to talk about the integration between Python, one of the most powerful languages, and PostgreSQL, the most powerful database in the open source world today. The subject, integration between Python and PostgreSQL, a programming language and a database, is very similar to the subject of the conference today, rock and roll and software development, which generally doesn't have any connection. In the same way, it's very rare to find somebody who's very good both at programming software and database development. It takes a different mindset to program code and to program databases. Each one has its own set of solutions and its own way to solve problems. I'm Zacks. I'm the CIO at CompuLab. We're a hardware company. We make two types of products. We make small computers for embedded devices and small computers for personal and industrial use. Our newest product is the microserver, which is a small computer built on quality server hardware. Our products take very little electricity, and that's their main draw besides their size. My department doesn't actually touch the products. We built an ERP system that integrates all of the different functionality of the company in order to help us build these wonderful products. Our system is built with a client desktop under the WX Python framework, a Django web client, and our database is PostgreSQL. PostgreSQL has some wonderful features. One of the main reasons why I chose it, and the subject of our discussion today, is the ability to write database functions in Python. What is PostgreSQL? Here we have the Python attacking the PostgreSQL and becoming a part of it. But what is PostgreSQL? Everybody recognizes MySQL, the most popular database in the open source world today. It's fast, sexy, a party animal. Everybody wants to use it. But there's a good chance that it'll drink too much one night, and the next morning when it wakes up, it'll forget what happened yesterday. PostgreSQL is the ugly sister. Practical, dependable, full of features, and most important, reliable. PostgreSQL is an enterprise-level database. It competes with Oracle and SQL Server for users. You can rely on PostgreSQL with your mission-critical data. PostgreSQL is 100% community-owned. There's no big corporation behind it. That's not to say that there's no profitability surrounding PostgreSQL. There's plenty of companies that offer service, support, and building custom features for their customers. Companies like Red Hat, Enterprise DB, Second Quadrant, and others hire core developers on their staff in order to support the product. If you don't want to pay for support, there's a very active mailing list with the participation of the core developers. It's not rare to receive an answer to a question you wrote within half an hour from a core developer. If you need help even faster than that, or interactive help, you can go to the PostgreSQL IRC channel and get help instantly. PostgreSQL also allows you to write functions, database functions, inside with outside languages such as Python. There are two types of stored code in databases: functions and stored procedures. Functions return one result and can be used in any place inside the SQL code. In the select clause, for example, the function result is used to display data as if it was a field. And we know a lot of functions already. For example, there are aggregation functions such as sum and count. There's string functions such as upper, which will return the string that you give it in all uppercase. And you can write your own functions such as full name, which will take two parameters, first name and last name, and return it back as both of them together with a space in between them. A stored procedure, on the other hand, can return an entire data set, and it can only be used in the from clause. They're written in the same under the same. Hello. They're written in the same footprint using the same function declaration, but they're not interchangeable. If you try to use a stored procedure function in any place other than the from clause, it'll give you an error. There are four types of SQL functions that you can write within PostgreSQL: SQL, PLPGSQL, trusted languages, and untrusted languages. This here is the function declaration where you put the function name here and the parameters. Set of means it returns more than one, the data type, and then over here you put in the language name. SQL functions are written in SQL syntax. It's basically a bunch of different statements written one right after the other and executed in order. It's the fastest way to write SQL code is in regular SQL, and it's run in one transaction. So either everything in the transaction happens or none of it happens. PLPGSQL is like SQL on steroids. It has control structures, if and else, loops, variables, dynamic execution, error handling, and things like that. Trusted languages and untrusted languages. The trusted part is not talking about the trusted level of the code or the language or even the level of execution. It's talking about the environment. Trusted languages do not have any. There we go. Trusted languages do not have access to the environment. They only have access to things within the database. They can't access file functions, operating system, network. If you try to write a file function such as open, it will give you an error. And it only has access to a limited set of libraries. The goal of using a trusted library is to use the power of the language to do things that would be very difficult to do in SQL. For example, if we have a function that receives a string parameter in the format of a JSON, and you want to stick all of the variables in the JSON into the database. So we're going to use a standard Python function, import JSON, load it into the variable, and then use a for loop to parse that and stick the variables into the database. Obviously, if you're doing this for real, you're going to want to check that the variables are appropriate and that the structure is appropriate. But for this example, this is fine. To do this sort of work in SQL itself would be absolute hell. So this is a very nice example, and you might look at it and say, well, that's cute, but you don't actually need integration in the database. Is this better? You might think that's nice and cute, but you don't actually need integration into the database in order to do that sort of thing. You can use one of the other libraries, such as PostgresQL or CyclePG, to access the database from outside. But there's a much tighter integration with PostgresQL, and one example is constraints. A constraint in the database is a way of forcing a specific field to only accept a certain type of data. A good example of a standard constraint that everybody knows is foreign keys. If you use a foreign key, the database will not let you put in a value into the child table that is not in the parent table. Using the way that a constraint works is it can call a function to check if the data is valid. So if we had a function or a field that we wanted to only include JSON data, we could write a function that basically checks if the value that we're loading in is a JSON. And using this try except code, if it is a valid JSON, it will return true, and then the database will let it in. And if not, it will return false, and then the database will throw it out and say you can't actually do that. So this is a very tight integration with the database using the power of Python in order to protect the data so that it only keeps the type of data that you want inside the fields. Another example where using PL Python would be very valuable is in triggers. Triggers in PL Python are much more flexible than in SQL. A trigger is an action that happens whenever you update, insert, or delete from the database. There we go. In triggers in PostgreSQL, there are new and old variables. Well, in an insert trigger, there's only a new. In delete triggers, there's only an old, and in update triggers, there's a new and an old. And the new and the old variables contain the record variable of the record that you just updated with all of the data. So in an update, for example, it's going to say new.fieldName is going to be the new value that you just changed, and old.fieldName is going to be the old value that you just put in. In PL Python, these are dictionaries. So you have dynamic access to the record, and you can then choose. You can dynamically access the various fields in there. So we wanted to build an audit trail in order to check all the different changes that happen in the database. So in our audit table, we wanted to have one audit table for the entire database, which would contain the following fields: the table name, the primary key value, the change type if it was an insert, update, or delete, field name, old value, and new value, and then obviously the change by. In PLPGSQL, to do this, you can't dynamically access the field names within the variable. So you would have to do, for example, if new.price is distinct from old.price, then insert that one into the audit table. Next field. If new.f1 is distinct from old.f1, insert that one into the audit table, and so on and so forth. You would have to do this for every single table. You would have to build a separate audit function going through each one of the fields. As you can see in PL Python, to do that same thing, you would basically use a for loop going through the keys of the dictionary, which have the variable names. Therefore, you can write one function for the entire database, and then every time you get a new field, all you have to do is say, I want the trigger on this table to access that function, it automatically works. You don't have to do any other coding. Now, until version 7.4 of PostgreSQL, there are both the trusted and the untrusted versions available of Python in PostgreSQL. In version 7.4, they decided that there were so many ways to find workarounds and to overcome the limitations of the trusted environment that they decided to drop it completely. Instead of trying to fight to maintain some level of security, they dropped it, which means that you can still write all of that code, but only in an untrusted environment. So what untrusted environment means is, once again, it doesn't have anything to do with the reliability of the code or the execution. It's talking specifically about the access to the environment. You have full access to the file system, to the operating system, and to the network. Also, you have access to all of the other modules of Python. Generally, a database operates in an independent environment. It's not connected to anything outside. Using an untrusted environment breaks down these walls and allows you to make your database into a component of the server instead of into its own entity by itself. Because of this, only the super user can create functions in an untrusted environment. The permissions that the Python code runs under is the permissions of the user that started the PostgreSQL daemon, not the user who is running the code. So if root starts the daemon and there's a database function that says rm minus rf slash, then you're going to wipe out the entire file system. It's very important to make sure that the user who starts PostgreSQL only has the limited amount of writes that he needs and no more than that. An example of code in the untrusted environment is very simple: writing data to a file. So we have code that says select star from sales, give me all the sales records for a specific customer, and write them down in a specific format, stick it onto the into the database. Doing this in SQL is difficult. There's generally a function here or there that allows you to write things to code, that you can choose specific formats, CSV, things like that, but writing it in your own format is generally very difficult to do. Obviously, this is a very simplistic example, and you can do much more powerful things, such as using ReportLab to generate actual graphs, reports, and fun stuff like that. So how do we use Python in the PostgreSQL? We get back to the original function. The code goes inside the function body over here. It uses standard Python syntax, including indentation. Just like in every Python function, you can't mix spaces and tabs. There's a, down here at the bottom, the language name, you would write PL Python U. PL is programming language, Python, the name of the language, and U, untrusted environment. If it was a trusted environment, it would have been PL Python. When they removed the trusted environment from Python, they didn't remove it from all the other ones. So for example, you can access Perl in a trusted environment, and it would be called PL Perl. There's a interface to the database called PLPy, as we saw in the last example. You call plpy.execute in order to access the database and to write SQL code. It has access to the, as I said, to the operating system, to the file system, to the network, and everything else. So this is all nice, but how does that help me out with a complete solution? So one thing that we might want to do, a standard feature request, is to send an email to the customer as soon as you get the order into the system. So what we would want to do is add a record to the table, have that immediately send the email, and we want to mark down in the system when the email was sent. So we would build a trigger on the sales table. Every time the sales new record is added to the sales, we call the function email customer. And we're going to do this in a before trigger because we want to update the table with the date of the sending of the email before we finish the transaction. The function email customer here calls a function to get the details of the email. Then it calls a function send email, and then it updates new.email sent date using the new variable to put in the date that happens. And this is a function written in PL/PGSQL because it uses variables. The function send email is written as a standard function that's written inside the database, and it uses the standard SMTP lib to send the email. So now we have a perfect solution that integrates everything into one nice package. Except that's problematic because even when you're writing software code inside the database, you still want to follow database principles. One of the database principles is called atomicity, which means that everything in a transaction has to be saved and occur, or nothing happens. In this example that we have a number of different problems. First of all, we don't want to rely on the email, or we don't want the saving of the sales record to depend on sending of the email. So if there's a problem with the email sending, we don't want to say we're not accepting sales records right now. Another problem is if the email did get sent and then the system crashed, then the email is still sent. We can't roll back that type of transaction. So what we want to do instead is, instead of sending the email on the transaction, we want to build an email details table, which includes all the details you want to send. It also includes a flag that says whether you want to send it or not, and the date that it was sent. Then you use a cron job to call a function inside the database to check the table every X minutes, let's say every 5 minutes, checks the database. If there's anything it needs to send, it then goes ahead and sends it. This solution will not only work for this, it will work for the entire application scope. So any function that needs to send emails can use that same logic. And now we have a solution that works with the database principles and with the power that's afforded in the programming language in order to do all of that. Now that we have a complete way of working, we have another problem, is that everybody works within their own application model. And this is a new animal. How are you supposed to be able to integrate this inside your application space? First of all, Mark Twain wrote, "I've never let my schooling interfere with my education." In other words, just because a box exists doesn't obligate you to lock yourself inside of it. The most popular application model today is the three-tier architecture. In the three-tier architecture, there's a separation between the presentation layer, the business logic, and the database. As we saw, sometimes you have to blur the lines between what's considered business logic and what's considered data. For the example of sending mail to the customers, we want to do that as one action. Using PL Python within the database gives us the opportunity to build a fourth layer. It's actually called N-tier architecture, not just three-tier architecture. So we'll build a fourth tier called data logic. Anything that has data integrated with actions will sit inside the database, and everything that is not tightly integrated with the data will sit on the application server. Most desktop applications are built with client-server applications, with the client-server model. When all of the actions are sitting on the desktop, you've got a number of problems. You have the opportunity for a number of problems, and you always have to check the configurations, the definitions, the format of the date, for example, in order to make sure that things don't happen. The reason why, or one of the reasons why people don't use an application server on desktop applications is because aside from the Java server, there's very few application servers that work with a desktop model. Using Python within PostgreSQL gives you the opportunity to have an application server, and that will close the gap between client server and three-tier architecture. Other examples of when this is appropriate is you have requirements that are not dependent on user actions. For example, we built a system to manage maintenance on machines in the company. The way that it works is that every machine has every machine has a date of maintenance, or a number of days after the last date of maintenance that it has to have maintenance again. So what it does, it's supposed to send an email when it comes to the time of maintenance. It sends an email or an SMS to the guy who's in charge of the machine. Generally, you would write this with a server-side script, or with a server-side script or a program, and then you have problems of maintenance. You have to back it up. You have to use version control, other things like that. A system like cron in order to call it. Putting that type of data, that type of function inside the database solves most of those problems, while you still need a scheduling system like cron in order to call the application. All of the rest of the issues are taken care of with the same way you do that with the rest of the database, scheduled backups and all of that. So I said that you can use PostgreSQL as an application server. What does that mean? An application server, am I supposed to switch slides? No. An application server is a platform that runs on the server and does actions according to the request of the client. It has access to the shared file system. Any change of code will have to happen immediately for all the clients without them having to reload the data. It's client agnostic. You write your code once, any client that connects to it can change or will get the same exact results. PostgreSQL, or Python with PostgreSQL, answers all of these requirements. The architecture of PostgreSQL is also appropriate for this. PostgreSQL is a multi-process system. Every connection gets its own process. It's not multi-threaded. So there's no possibility of runaway Python code crashing your database server. It's running in its own process. If there's a problem with that, you kill that process, and the rest of the database is still running as is appropriate. So now that we've learned how this all works, let's look at some actual code. Here's an example where we are going to send an FTP file, or a function that FTPs files from within the database. You pass it in the name of the file you want to pass. We're going to put this inside the data logic schema. I'm going to explain what a schema is in another minute. Use a standard FTP file function to send the file. Interacting with the database here with the plpy.execute module, but without writing any SQL code, because we want to separate the SQL from the business function. And then on the bottom we have another SQL code, or another code that calls SQL, which is going to write the error to a table. The getSetting function is a SQL function. As we can see here, it's a language SQL, and that talks directly to the database. Another example is it's possible to create a form of replication where you can connect to another outside database. In this case, we are calling a function called export customers, It gets us all of the list of customers we want to put on a remote server. And then we connect to a MySQL database on a remote server using that same get settings in order to find out what the server name is. And then it goes through and it puts all of the data into the MySQL table over there. And now we have an integrated replication function. What else can PostgreSQL do? Or PostgreSQL with Python do? We use it to add data to an iCalendar server, call shell functions. We use PyCurl for website processing, generate and save reports, or in short, anything that you can do with Python. It's completely unlimited. So what shouldn't you be doing? First of all, you have to always remember to separate your data logic from your interaction with the data itself. You want to make sure that you're not PHPing your code. PostgreSQL has a logical division called a schema, which allows you to decide where everything goes. So the getSetting function that I mentioned before was in the public schema. Everything can access that. The FTP file was in the data logic schema. So now if you want to update some code, you know exactly where to go to find it. You don't have to be searching through your system. You have to make sure that you keep your presentation, your layers separate, so that it's much easier to maintain. And there's a big desire, especially for code designers, to start to write all functions in Python. As soon as you know that you can do it, then you're going to want to do it. Don't do that. Only use Python for examples when it's the perfect solution for that case. I wanted to share a piece of really, really cool code that I wrote that you really should not do. Sometimes you start running a database function, and in the middle of the function, it gets to a point where it needs user input. So generally what you do is you return an error code. The client then asks the user if he wants, what he wants to do. You pass it back, and then the function starts again with some sort of approved code. I just thought that it would be very cool if the database didn't have to start again from scratch and could just start right where it left off. So I built a socket server inside the client. And every client would then start off with a socket server in its own thread. And then on the database, I wrote this function here, the Python prompt, which connects to the socket server on the client side, or on to the IP address that called the function. It then sends the question. The client pops up the question. He hits yes. It immediately goes back to the database. There's a timeout code of 120 seconds, so it waits 2 minutes to get a response. Basically, the function waits there for 2 minutes. If it doesn't get any response after 2 minutes, it cancels out the request. If it does get a response, then it will keep on going, and therefore it doesn't have to start again. Obviously, this is very dangerous because, first of all, it's not client agnostic. Every client has to have the socket server built inside. It's not separating from the different presentation layers because your GUI code is dependent on the database itself. So while it is very cool, it's not something that should be done. While I was playing with this, somebody showed me this very cool website called SQLonRails.org. SQL on Rails taking the VC out of MVC. Model. SQL on Rails is an open source web framework that's optimized for language consolidation and breakneck collaboration. So select SQL on Rails and get your application on the fast track. I recommend everybody to go and look at this website. They've got a great YouTube video or presentation showing how you change GUI code inside your database. It's very, very cool. It certainly stresses the point of not using every tool you have for every single purpose. Thank you very much.